I've been thinking about what existed before the Big Bang, and, well, it's one of those questions that seems straightforward at first, doesn't it? I mean, something happened, right? The universe began, there was this moment of creation, this cosmic explosion that started everything. So naturally, you'd think, okay, what was there before that moment? What existed in the time before time, in the space before space? And that question, that simple, obvious question, turns out to be one of the most profound, most perplexing, most reality-bending puzzles in all of science and philosophy. Because the answer, if there even is an answer, forces us to completely reimagine what we mean by words like before and existence and beginning itself. You see, when we ask what came before the Big Bang, we're bringing our everyday understanding of time to a situation where it turns out that understanding completely breaks down. We're used to time working in a very particular way, right? There's a past, a present, a future. Events happen in sequence. Every moment has a moment before it. Every effect has a cause. It's how we experience reality, how we make sense of the world. If you watch a movie, you know there was a scene before the current scene. If you're born, there was a time before you were born. If something begins, there was something before it began. That's just, that's just how things work, or at least that's how we think they work. But the Big Bang, well, it's not like other beginnings. It's not like lighting a candle or starting a race or turning on a computer. Those things happen within time, within space. They're events that occur in an already existing framework of reality. The Big Bang, though, if we understand it correctly, and that's a big if, isn't just the beginning of stuff. It's the beginning of the framework itself. It's the beginning of time, the beginning of space, the beginning of all the physical laws that govern how anything can happen at all. And if time itself began with the Big Bang, then the whole concept of before, which is a time-based concept, starts to fall apart. It's like asking what's north of the North Pole. The question seems meaningful, but when you really think about it, when you really understand what the North Pole is, you realize that the question doesn't actually make sense in the way you thought it did. And that's frustrating, isn't it? Because we want to know. We have this deep, fundamental need to understand where we came from, where everything came from. It's built into us, this curiosity about origins. Every culture, every civilization has creation myths, stories about how the world began, what was there in the beginning. Some say there was chaos, primordial waters, endless void. Some say there was nothing, absolute nothing, until a divine force brought something into being. Some say the universe has always existed in one form or another, cycling through death and rebirth, expansion and contraction. These aren't just ancient superstitions. They're humanity's attempts to grapple with what is genuinely one of the deepest mysteries we can conceive of. And now, in the modern era, we have science, we have mathematics, we have observations of the cosmos itself, and yet the mystery remains. In some ways, it's gotten deeper, stranger, more unsettling. The thing is, when scientists talk about the Big Bang, they're not talking about an explosion that happened somewhere in space. That's the first misconception we need to clear up, because it colors how we think about everything else. In the popular imagination, and I've seen this in countless diagrams and animations and textbooks, the Big Bang is depicted as this point in the middle of darkness, this concentrated ball of energy and matter that explodes outward into a pre-existing void. And that image, while it's useful in some ways, is fundamentally misleading, because there was no pre-existing void. There was no space for the explosion to happen in. Space itself, all of space, emerged from that initial state. It's not that the universe is expanding into something. It's that space itself is stretching, growing, creating more of itself as it goes. So if you try to picture it, if you try to imagine the universe at its very beginning, you can't think of it as a tiny, dense point sitting in blackness. You have to think of it as, well, as everything, all of space, no matter how vast the universe is now, was compressed into that initial state. And I know that's hard to wrap your mind around because we're spatial creatures. We exist in 3 dimensions. We navigate through space. We understand things by their locations and their distances from other things. But at the beginning, there was no outside, no elsewhere, no other location. There was just that one state containing everything that would ever be. And time is even stranger. Because if the Big Bang was the beginning of time itself, then asking what happened before it is like asking what happened before the first moment. It's a logical impossibility, right? If there's no time before the Big Bang, then there's no before in which anything could happen or exist. Some physicists describe it this way: time is a dimension of the universe, just like the three spatial dimensions we're familiar with. And just as space had a beginning at the Big Bang, so did time. The universe doesn't exist in time the way we might think of an object existing in a room. Time exists in the universe as part of its very structure. So the Big Bang isn't an event that happened at a particular time. It's the event that created time, that brought time into being as a dimension of reality. Stephen Hawking used to explain it with this analogy about the North Pole, and it's really quite elegant. He'd say, imagine the universe as the surface of a sphere, like the Earth, and imagine time as a direction on that sphere, like latitude. If you start at the equator and move north, you're moving through time, moving toward earlier and earlier moments in cosmic history. And you can keep going north, tracing back through billions of years, getting closer and closer to the beginning. But eventually you reach the North Pole. And at the North Pole, there is no more north. The concept of north doesn't extend beyond that point. It's not blocked by a barrier or a wall. It's that the direction itself terminates. And in the same way, as you trace time backward toward the Big Bang, you eventually reach a point where time itself begins, where the concept of earlier no longer applies. There is no before, not because something prevents you from going there, but because the dimension of time doesn't extend in that direction. But here's the thing, here's what makes this so complicated and so fascinating. The Big Bang, as we understand it through Einstein's general relativity and our observations of the cosmos, points toward this moment of beginning, this singularity where all the matter and energy and space and time of the universe were compressed into an infinitely small, infinitely dense point. And that's what the mathematics tells us when we run the equations backward, when we reverse the expansion of the universe and watch everything collapse back toward the origin. We get this singularity, this point of infinite density, infinite temperature, infinite curvature of space-time. And whenever you get infinities in physics, whenever your equations spit out infinity as an answer, that's usually a sign that something's wrong. Not wrong with reality, but wrong with your theory, your description of reality. It means you've pushed your equations beyond their range of validity into a realm where they can no longer accurately describe what's happening. And that's where we are with the Big Bang. General relativity, which is our best theory of gravity and space-time, works brilliantly for describing the universe as it is now and as it was in the past, going back pretty far toward the beginning. But when you get really close to that initial moment, when you get to the Planck time, which is about 10 to the minus 43 seconds after the Big Bang, an incomprehensibly tiny fraction of a second, the theory breaks down. At that scale, quantum effects become important, dominant even. And we don't have a complete theory of quantum gravity, a framework that successfully merges quantum mechanics with general relativity. So we hit a wall. We can trace the history of the universe back to a fraction of a second after the beginning, but that last tiny interval, that moment of the beginning itself, remains shrouded in mystery. Now, does that mean we can't say anything about what might have existed before? Well, not necessarily. Because even though we can't describe the singularity itself, even though our equations fail us at that point, we can still think about it, speculate about it, develop theories and models that might apply. And physicists have come up with several really intriguing possibilities. These aren't proven theories, not yet. They're more like frameworks, hypotheses, different ways of thinking about the problem. But each one offers a different perspective on what before the Big Bang might mean, if it means anything at all. One of the most mind-bending ideas comes from quantum mechanics itself. You see, in the quantum realm, the realm of the very small, particles and energy behave in ways that seem impossible according to our everyday experience. One of the fundamental principles of quantum mechanics is the uncertainty principle, discovered by Werner Heisenberg in the 1920s. It says that there are limits to how precisely you can know certain pairs of properties at the same time. The more accurately you know a particle's position, the less accurately you can know its momentum and vice versa. And there's another pairing that's equally important, energy and time. The uncertainty principle tells us that over very short time scales, energy can fluctuate wildly. The universe, at the quantum level, is seething with these fluctuations, these temporary violations of energy conservation that pop in and out of existence too quickly for us to directly observe. And this leads to a fascinating idea. Maybe the universe itself is a quantum fluctuation. Maybe the Big Bang, the beginning of everything, wasn't caused by anything external. Maybe it just happened spontaneously, the way particles spontaneously appear and disappear in the quantum vacuum. In the 1970s and 80s, physicists like Edward Tryon and Alexander Vilenkin explored this possibility. Tryon famously said, "The universe is simply one of those things that happens from time to time," which sounds flippant, but it's actually a serious scientific proposal. If the total energy of the universe is zero, and it might be if you add up all the positive energy from matter and radiation and all the negative energy from gravity, then the universe doesn't violate energy conservation by existing. It's a quantum fluctuation that doesn't have to pay back any energy debt, so to speak. It can persist indefinitely. But if that's true, if the universe came from a quantum fluctuation, then what was there for it to fluctuate from? What was the quantum vacuum that gave birth to space and time? And here's where it gets really strange. Some physicists argue that there was no before in the conventional sense, that there was a different kind of reality, a quantum state that existed independently of time as we know it. In this view, time is an emergent property, something that arises from deeper quantum processes. Before the Big Bang, or rather, in the state from which the Big Bang emerged, there might have been a timeless quantum realm, a mathematical structure where all possibilities exist in superposition, where the normal rules of cause and effect don't apply. Vilenkin's model describes the universe as tunneling into existence from nothing. In quantum mechanics, particles can tunnel through barriers that they classically shouldn't be able to cross. An electron, for instance, can suddenly appear on the other side of a wall without having passed through it, if the wall is thin enough. It's a purely quantum effect, predicted by the wave function. And Vilenkin suggests that the universe did something similar. It tunneled from a state of nothing, no space, no time, no matter, into a state of something, a tiny universe that then began to expand and evolve according to the laws of physics. The boundary condition, the initial state, is literally nothing. Not empty space, because space is something, not a pre-existing quantum field, because fields are something, but true nothingness, the absence of any physical reality whatsoever. Now, you might object to this. You might say, wait, how can something come from nothing? Doesn't that violate the principle that effects must have causes? Doesn't it contradict the most basic logic? And you're right to be skeptical. But here's the thing. The principle of causation, the idea that every event must have a prior cause, is based on our experience within time. It's a rule that seems to govern how things work in the universe as we know it. But if time itself had a beginning, if causation is a feature of temporal reality, then it might not apply to the origin of time itself. The universe as a whole might not need a cause in the traditional sense, because the very concept of causation depends on temporal sequence, on befores and afters, and at the boundary of time, those concepts break down. There's another possibility, another framework that some physicists find compelling. Instead of the universe beginning from nothing, maybe it emerged from something else, something that exists in a different sense than our universe does. This is the idea behind eternal inflation, proposed by Alan Guth and refined by Andre Linde and others. The core concept is that the Big Bang, our Big Bang, wasn't the beginning of everything. It was just, it was just one event in a much larger, possibly eternal process. Inflation theory, which we'll get into more deeply in a moment, posits that the early universe underwent a period of exponentially rapid expansion, driven by a special kind of energy field called the inflaton field. In a tiny fraction of a second, the universe expanded by a factor of at least 10 to the 26, smoothing out irregularities and setting the stage for the more gradual expansion we observe today. Eternal inflation takes this idea and extends it. It suggests that inflation, once it starts, can never truly end everywhere. Sure, in our region of space, inflation stopped. The inflaton field decayed, its energy converted into particles and radiation, and that decay is what we call the Big Bang. But in other regions, vastly far away, inflation might still be going on. And in fact, inflation might be constantly creating new regions of space where it stops new pocket universes or bubble universes that each have their own Big Bang. In this picture, the multiverse, and I know that term carries a lot of baggage, a lot of controversy, is eternal. There's no overall beginning. Inflation has been going on forever into the past and will go on forever into the future, constantly spawning new universes. Our Big Bang was just the moment when inflation stopped in our particular bubble, our particular region. Before our Big Bang, in the sense of what existed in the broader multiverse, there was the eternally inflating quantum field churning out universes without end. But wait, you might ask, if inflation is eternal into the past, doesn't that solve the problem? Doesn't that mean there was no beginning, that something has always existed? Well, sort of, but not quite, because even eternal inflation, according to a theorem proved by Arvind Borda, Alan Guth, and Alexander Vilenkin in 2003, can't actually be eternal into the past. If the universe has been expanding on average, which it must be if inflation is occurring, then you can't trace it back infinitely far. There must be some kind of boundary in the past, some point beyond which the classical description breaks down. So even the multiverse, if it exists, seems to require some kind of beginning, or at least a boundary that we can't see beyond with our current theories. And this brings us back to the fundamental problem. No matter which way we turn, no matter which theoretical framework we adopt, we seem to hit a wall. Either time began, in which case there's no before, or we need a quantum theory of the beginning, which we don't yet have. Or the universe emerged from some prior state, but then we have to ask what that state was and where it came from. It's like peeling an onion. Each layer reveals another layer underneath, and we never quite reach the core. Some physicists have explored the idea that time might be cyclical, that the universe goes through endless cycles of expansion and contraction, big bangs and big crunches, death and rebirth. This is an old idea, actually, present in Hindu cosmology and in various other philosophical traditions. But modern versions try to ground it in physics. Roger Penrose, one of the most creative thinkers in cosmology, has proposed something called conformal cyclic cosmology. His idea is that the universe will eventually expand forever, and as it does, it will become increasingly empty, increasingly cold. All the matter will decay. All the black holes will evaporate through Hawking radiation, and what's left will be just photons and other massless particles flying through empty space. And in that state, he argues, the universe loses its sense of scale. There's nothing to measure distance or time against. And mathematically, that final state of our universe could be equivalent to the initial state of a new Big Bang. The end becomes the beginning, and the cycle repeats. It's a beautiful idea, elegant in its symmetry. But it faces challenges. For one thing, the universe is accelerating in its expansion, driven by what we call dark energy. And current observations suggest that this acceleration will continue forever, that the universe won't collapse back in on itself. So if there are cycles, they don't look like oscillations between expansion and contraction. They'd have to be something more subtle, more complex. And Penrose's model requires some very specific conditions to be met. It's not clear yet whether those conditions actually hold in our universe, but the fact that serious physicists are even considering these cyclical models tells you something about how far we're willing to go, how creatively we're thinking, to grapple with the question of cosmic origins. Then there's the possibility that comes from string theory and M theory, these frameworks that try to unify all the forces of nature by describing particles not as points, but as tiny vibrating strings of energy. String theory requires extra dimensions beyond the 3 of space and 1 of time that we experience. 6 or 7 additional dimensions depending on the version, curled up so small that we can't perceive them directly. And in some versions of string theory, particularly M theory, the universe might be a 3-dimensional brain floating in a higher dimensional space called the bulk. And if there are other brains, other universes floating in the bulk, they might occasionally collide. And when they collide, the energy released could be enormous, sufficient to create a Big Bang, a fireball of particles and radiation that would look from the perspective of beings living on that brain like the beginning of the universe. In this scenario, what existed before the Big Bang? Well, there were these higher dimensional structures, these brains in the bulk, existing in some prior state. And the collision of brains wasn't the beginning of everything, just the beginning of our observable universe. Before the collision, the brains existed, and they might collide again and again, creating an endless series of big bangs, each one looking like the beginning from the inside, but actually being part of a larger cosmic cycle. It sounds like science fiction, doesn't it? And maybe it is. The challenge with all of these ideas, quantum fluctuation, eternal inflation, cyclical cosmology, colliding brains, is that they're extraordinarily difficult to test. We can't see past the cosmic microwave background, the radiation left over from when the universe was only 380,000 years old. That's our observational horizon. Anything that happened before that is hidden from us, not by some physical barrier, but by the fact that the universe was opaque to light before that time. The early universe was so hot and dense that photons couldn't travel freely. They were constantly scattered by free electrons. Only when the universe cooled enough for atoms to form did light begin to travel unimpeded through space. And that first light is what we see in the cosmic microwave background. So we're trying to understand the first fraction of a second of the universe, the moment of the Big Bang itself, based on evidence from much later. It's like trying to understand someone's birth by interviewing them when they're 30 years old. You can infer a lot, you can reconstruct the story, but you're always working with indirect evidence. And for the moment before the moment, for the state that preceded the Big Bang, we have even less to go on. We have mathematics, we have theoretical consistency, we have philosophical arguments. But direct observational evidence, that's elusive. Still, physicists haven't given up. They're looking for subtle signatures, predictions that different models make about the cosmic microwave background or about the distribution of galaxies or about gravitational waves. For instance, inflation makes specific predictions about the patterns of temperature fluctuations in the cosmic microwave background, and those predictions have been confirmed with remarkable precision. That gives us confidence that something like inflation happened. But which version? The eternal version? The quantum tunneling version? We don't know yet. And theories about what came before or what exists outside our bubble make predictions that are incredibly hard to verify. There's also the problem of what we mean by nothing. When physicists like Lawrence Krauss write books titled A Universe from Nothing, they're using nothing in a specific technical sense. They're talking about the quantum vacuum, a state with no particles, no matter. But the quantum vacuum isn't truly nothing. It's a seething sea of virtual particles, a state governed by the laws of quantum field theory embedded in space-time. It has structure, properties, rules. Philosophers rightly point out that this isn't the same as philosophical nothing, the complete absence of anything whatsoever, including physical laws and space-time itself. So when we ask whether the universe came from nothing, we have to be careful about what we mean. Can something come from truly nothing, from the absolute absence of any physical reality or mathematical structure? Honestly, we don't know. It might be a question that doesn't even make sense, because the moment you ask what something came from, you're already assuming a framework of causation and temporal sequence. And that framework might be internal to reality, not external to it. The universe might not need an external cause or a prior state, because those concepts only make sense within the universe. But then, if we accept that the universe might have just begun to exist without a cause, without a prior state, we're left with this profound sense of mystery. Why does anything exist at all? Why this universe, with these laws of physics, these constants of nature? Why is there something rather than nothing? And here we venture into philosophy, into questions that might not have scientific answers, at least not answers that we can test and verify. Some physicists invoke the anthropic principle, which comes in several forms, but basically says that we observe the universe to be the way it is, because if it were significantly different, we wouldn't be here to observe it. The constants of nature, the strength of gravity, the mass of the electron, the cosmological constant, seem finely tuned for the existence of stars, planets, chemistry, life. Change them even slightly, and you get a sterile universe, a universe where complexity can't emerge. Is this fine-tuning evidence of design, of a creator who set the parameters just right? Or is it evidence of a multiverse where every possible combination of constants exists somewhere, and we happen to find ourselves in one of the rare universes where life is possible? The anthropic principle doesn't tell us what existed before the Big Bang, but it does address why our universe has the properties it does. And in the context of eternal inflation or colliding brains, where countless universes might exist with different laws and constants, the anthropic principle becomes almost a necessary explanatory tool. We're here in this universe because this universe allows us to be here. In the vast majority of universes, there's no one asking these questions. But that explanation, while logically coherent, feels somewhat unsatisfying, doesn't it? It pushes the mystery back but doesn't eliminate it. We still want to know why there's a multiverse, where the laws of quantum mechanics and inflation come from, why anything exists at all. And maybe those questions don't have answers. Maybe they're the wrong questions, formulated in terms that don't apply to the ultimate nature of reality. There's a philosophical tradition that says existence is necessary, that the question, why is there something rather than nothing, is misguided, because nothingness is actually impossible. If you define nothing as the absence of everything, including the absence itself, then nothing is an incoherent concept. It can't exist, even in principle. Something, some form of existence, is inevitable. And maybe that something is a quantum field, or a mathematical structure, or a consciousness, or a multiverse. We don't know. But the idea that pure nothingness is impossible, that existence is necessary, offers a different way of thinking about the problem. Of course, that just raises new questions. What determines the nature of the necessary existence? Why these laws, these structures, and not others? Are the laws of physics themselves necessary, or are they contingent, just one possibility among many? String theory suggests that there might be a vast landscape of possible universes, each with different physics, and the laws we observe are just one point in that landscape. But where does the landscape itself come from? What meta-laws or meta-structures determine what's possible? Some theorists, like Max Tegmark, have proposed that all mathematical structures exist, that the universe is fundamentally mathematical, and every consistent mathematical structure corresponds to a real universe somewhere. In this view, physical existence and mathematical existence are the same thing. The universe doesn't just obey mathematical laws, it is those laws realized. And if every mathematical structure exists, then the question of why our particular universe exists is answered. All possible universes exist, and we're simply in one of them. But again, this just shifts the mystery. Why does mathematics exist? Why is there a realm of abstract structures at all? I find myself going in circles, and I suspect that's inevitable when we're dealing with questions at the absolute boundary of knowledge, and perhaps beyond. We're asking about the origin of space, time, matter, energy, causation itself. We're asking about the framework within which all questions are normally formulated. It's like trying to see your own eyes without a mirror. We're inside the system, trying to understand the system from within, and yet we keep trying, because that's what humans do. We push against the boundaries, we ask the questions that seem unanswerable, we develop new tools and new concepts to probe deeper. A few hundred years ago, we didn't know that the universe was expanding. We didn't know about the Big Bang. We didn't have quantum mechanics or general relativity. Our understanding has grown tremendously, and it continues to grow. Right now, we're in an interesting moment in cosmology. We have a standard model, a framework called the Lambda CDM model, that describes the universe's history from a fraction of a second after the Big Bang to the present day. It matches observations remarkably well, but it also has deep mysteries embedded in it. Dark matter, which makes up about 27% of the universe's mass energy, is completely unknown. We don't know what it is. Dark energy, which makes up about 68% and drives the accelerating expansion, is even more mysterious. And the Big Bang itself, the singularity at the beginning, is a place where our theories break down. Physicists are working on these problems. They're building more powerful telescopes to observe the early universe in greater detail. They're constructing particle accelerators to probe the fundamental forces at higher energies. They're developing new mathematical frameworks, new theories that might unify quantum mechanics and gravity. And maybe in the coming decades or centuries, we'll have answers. Maybe we'll understand what existed before the Big Bang, or we'll realize that the question doesn't make sense, or we'll discover something entirely unexpected that reframes the whole discussion. One of the things I find most fascinating about this quest is how it forces us to question our most basic assumptions. We assume that time flows in one direction, from past to future. We assume that causation works forward in time, that causes precede effects. We assume that space is a container in which things exist. that the universe is embedded in something larger. But all of these assumptions might be wrong, or at least they might be approximations that work well in our everyday experience, but fail at the extremes. Time, for instance. Einstein showed that time is relative, that it flows at different rates depending on your motion and the gravitational field you're in. Near a black hole, time slows down dramatically compared to far away in flat space. And in some solutions to Einstein's equations, time can loop back on itself, creating closed time-like curves where you could, in principle, travel to your own past. Most physicists think these solutions are unphysical, that quantum effects or other considerations would prevent actual time loops. But the fact that the equations allow them tells you that time is much stranger than we intuitively think. And in quantum mechanics, time is even more peculiar. The Schrödinger equation, which governs how quantum systems evolve, treats time as a parameter, not as an operator like position or momentum. Time is external to the quantum state, a backdrop against which quantum processes unfold. But when you try to apply quantum mechanics to the universe as a whole, you run into problems. There's no external time. The universe is all there is. So how do you describe its evolution? This is the problem of time in quantum gravity, and it's one of the most vexing issues in theoretical physics. Some approaches, like the Wheeler-DeWitt equation, seem to suggest that time doesn't exist at the most fundamental level, that it's an emergent phenomenon that arises from quantum entanglement, or from our limited perspective. If time is emergent, if it's not fundamental to reality, then the question of what existed before the Big Bang takes on a different character. Maybe there was a timeless quantum state, a superposition of all possible histories, and the universe we observe is one particular realization, one branch of the wave function. Before time existed, there was no before. There was only this timeless quantum realm, where all potentialities coexist. It's hard to think about, isn't it? Our brains are wired for time. We experience the world as a sequence of moments, each flowing into the next. The idea of a state without time, where everything just is, where there's no change and no sequence, is almost incomprehensible. But mathematics allows us to describe it, to work with it, even if we can't fully visualize it. And maybe that's the key insight. Maybe the universe at its deepest level isn't something we can visualize or intuit. Maybe it's fundamentally mathematical, describable only through equations and abstract structures. And our job as scientists, as curious beings trying to understand our origins, is to follow the mathematics wherever it leads, even if it takes us to places that defy our intuition. There's a certain humility required in this endeavor. We have to accept that we might never have a complete answer, that the question of what existed before the Big Bang might be beyond our capacity to fully resolve. But that doesn't mean we should stop asking. Every answer we find, every piece of the puzzle we fit into place, deepens our understanding. And even if we never reach the ultimate truth, the journey itself is worthwhile. The questions we ask, the theories we develop, the observations we make, all of this expands the horizons of human knowledge and enriches our sense of wonder at the cosmos. Consider what we've learned so far. We know that the universe is about 13.8 billion years old, give or take a few million years. We know this from multiple independent lines of evidence: the expansion rate, the cosmic microwave background, the ages of the oldest stars. We know that the universe is expanding and that the expansion is accelerating. We know that the early universe was incredibly hot and dense, a plasma of particles and radiation. We know that this plasma cooled as it expanded, allowing protons and neutrons to form, then nuclei, then atoms. We know that small fluctuations in the density of matter, imprinted during the inflationary epoch, grew over time under the influence of gravity to become galaxies, stars, planets. This is an extraordinary achievement, right? A century ago, we didn't even know that galaxies existed. We thought the Milky Way was the entire universe. Edwin Hubble changed that in the 1920s when he observed Cepheid variable stars in what we now call the Andromeda Galaxy, and realized it was far too distant to be part of the Milky Way. It was another galaxy entirely, one of billions. And then Hubble made an even more remarkable discovery. He found that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe is expanding. This was a shock. Einstein had assumed the universe was static, eternal, and unchanging. When his equations of general relativity predicted a dynamic universe, either expanding or contracting, he introduced the cosmological constant, a fudge factor, to keep it static. Later, he called this his greatest blunder, because the universe isn't static. It's been expanding since the Big Bang, and that expansion tells us that the universe had a beginning, a moment when everything was compressed into an unimaginably small, hot, dense state. Georges Lemaitre, a Belgian priest and physicist, was actually the first to propose this idea, which he called the primeval atom hypothesis. He suggested that the universe began as a kind of cosmic egg, a superdense concentration of matter and energy that exploded outward. The term Big Bang was coined later, actually as a dismissive insult by Fred Hoyle, an astronomer who preferred the steady-state model of the universe. But the name stuck, and the evidence mounted. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation, a faint glow of microwave radiation coming from every direction in the sky. This radiation is the afterglow of the Big Bang, the cooled remnant of the fireball that filled the early universe. Its discovery was the smoking gun, the definitive evidence that the Big Bang really happened. And since then, we've measured the cosmic microwave background in exquisite detail. We've mapped its temperature fluctuations to a precision of 1 part in 100,000. We've found that it matches the predictions of the Big Bang model almost perfectly. And those tiny fluctuations, those little variations in temperature, are the seeds of all the structure we see today. Regions that were slightly denser than average attracted more matter through gravity, growing over billions of years into galaxies and galaxy clusters. Regions that were slightly less dense became the voids between galaxies. The cosmic microwave background is a baby picture of the universe, showing it as it was when it was only 380,000 years old, before stars or galaxies existed. And encoded in that picture is information about the Big Bang itself, about the conditions in the first fraction of a second. But as detailed as our observations are, they can't take us all the way back. The cosmic microwave background is a kind of wall, a limit to how far we can see. Before that, the universe was opaque. Light couldn't travel freely. And before the first few minutes, the universe was so hot that even atomic nuclei couldn't hold together. Going back even further, to the first second, we're in a realm where the physics is less certain, where we have to rely on particle physics experiments and theoretical extrapolations. And before the first fraction of a second, before the Planck time, we're essentially in the dark. That's where quantum gravity becomes essential. And we don't have a complete theory of quantum gravity. We have candidates, string theory, loop quantum gravity, causal set theory, others, but none of them are fully developed or experimentally confirmed. So we're left with informed speculation, plausible scenarios, but not definitive answers. One of the intriguing things about inflation, which I mentioned earlier, is that it offers a mechanism for generating the initial conditions of the universe. Before inflation was proposed, physicists were puzzled by several features of the universe that seemed to require very special, finely tuned initial conditions. One is the horizon problem. The cosmic microwave background looks almost exactly the same in all directions. Different regions of the sky have almost identical temperatures, even though they're so far apart that light couldn't have traveled between them in the time since the Big Bang. How did they all end up at the same temperature if they couldn't communicate, couldn't exchange energy? Inflation solves this. If the universe underwent a period of exponential expansion very early on, then regions that are now far apart were once in close contact, in thermal equilibrium. They had the same temperature because they were part of the same small patch of space. Then inflation stretched that patch enormously, spreading those regions across vast distances. When we look at the cosmic microwave background, we're seeing the remnants of that once tiny, once connected region. Another puzzle is the flatness problem. Observations show that the universe is spatially flat, or very close to it. Space doesn't curve back on itself like a sphere, and it doesn't curve open like a saddle. It's flat, like an infinite plane, but a flat universe is an unstable equilibrium in the equations of general relativity. Any slight deviation from flatness in the early universe would have been amplified enormously by now. The fact that the universe is still so flat today suggests that it was incredibly, unbelievably flat at the beginning. Why? Inflation explains this too. The exponential expansion stretches out any initial curvature, making the universe flat, just as inflating a balloon makes its surface appear flatter to an ant walking on it. So inflation is attractive because it solves these problems and because it makes predictions that we can test. But it also raises new questions. What is the inflaton field? What caused inflation to start? What caused it to stop? And if inflation can happen once, why not many times? That's where eternal inflation comes in, the idea that inflation is constantly creating new bubble universes, new regions where inflation stops and a Big Bang occurs. And if that's true, then our Big Bang is just one event among countless others, our universe just one bubble in a vast multiverse. But even if eternal inflation is correct, it doesn't fully answer the question of what existed before. Because you can ask, where did the inflaton field come from? Where did the quantum vacuum come from? And some version of the beginning problem still arises. Maybe it's pushed back, maybe it's deferred, but it doesn't go away entirely. Unless, of course, the universe really is eternal, not just into the future, but into the past. But as I mentioned, there are theorems suggesting that even eternal inflation can't be past eternal if space-time has been expanding on average. There has to be some kind of boundary or beginning. So we're back to needing a quantum description of that boundary, that moment of origin. Loop quantum gravity, one of the alternative approaches to quantum gravity, offers an interesting perspective. In this framework, space itself is quantized, made up of discrete chunks called loops or spin networks. Space isn't continuous but granular, like a fabric woven from threads. And when you apply loop quantum gravity to cosmology, you get something called loop quantum cosmology, which predicts that the Big Bang singularity is replaced by a big bounce. Instead of the universe starting from a singularity, it might have rebounded from a previous contracting phase. The universe contracts, reaches a minimum size, not zero because of quantum effects, and then bounces back into an expanding phase. What we call the Big Bang is actually the bounce. In this picture, there was something before the Big Bang, a previous universe collapsing down, then bouncing back. Time might extend infinitely into the past, with an endless series of bounces, each one looking like a new beginning, but actually being part of a larger cycle. This is speculative, and the details depend on assumptions about how quantum gravity works in extreme conditions. But it's a fascinating possibility, one that avoids the singularity and provides a kind of answer to the before question. And yet, even if the big bounce model is correct, you can still ask deeper questions. Why does the universe bounce instead of collapse into a singularity? What are the quantum laws that govern the bounce? Where do those laws come from? The regress doesn't necessarily end. Maybe the regress can't end. Maybe every answer we find will raise new questions, and that's just the nature of reality. Or maybe there's a level where the questions stop making sense, where we reach the foundation and there's nothing more to explain. Philosophers have debated this for millennia. Some argue for an infinite regress of causes, each depending on a prior cause with no first cause. Others argue for a necessary being or a necessary structure that exists by its own nature and doesn't require explanation. And science, which has traditionally focused on efficient causes, what brought something about, might need to incorporate final causes, formal causes, or other modes of explanation that go beyond simple temporal causation. There's also the possibility that the very question, what existed before the Big Bang, is based on a mistaken assumption. Maybe time doesn't work the way we think it does. Maybe the universe isn't fundamentally temporal at all. In some interpretations of quantum mechanics, like the Everett many worlds interpretation, the universe is a vast superposition of all possible states, and time is just a way of describing how those states are correlated. The flow of time, the sense of moving from past to future, might be an illusion, a feature of our consciousness rather than a feature of objective reality. That sounds radical, I know. But there are serious physicists who take this seriously. If the universe is fundamentally a quantum wave function, a superposition of all possible configurations, then there's no objective present moment. All moments exist equally, spread out across the wave function. The Big Bang is one part of the wave function, and the far future is another part, and they're all equally real. Our experience of time, our sense of being at a particular moment and moving toward the future, arises from the way our brains process information and from the thermodynamic arrow of time, the fact that entropy increases. But if that's true, then asking what existed before the Big Bang is like asking what's to the left of the leftmost point on a map. The question presupposes a structure that might not actually exist. The Big Bang might be the earliest point in the wave function, not because time stops there, but because there is no earlier configuration in the superposition. The universe just is, timelessly, and our temporal perspective is a feature of how we're embedded in that timeless structure. I realize this is getting quite abstract, quite philosophical, but these are the kinds of considerations that come up when you really dig into the question. We're not just asking about events in the past. We're asking about the nature of time, the nature of existence, the nature of explanation. And those are deep, hard questions. They might not have clean, simple answers. What strikes me thinking about all this is how much we've learned and how much we still don't know. We've gone from thinking the universe is eternal and unchanging to realizing it had a beginning. We've measured that beginning to within a fraction of a second. We've mapped the cosmic microwave background, detected gravitational waves, discovered that the universe is accelerating. We've developed theories, general relativity, quantum mechanics, inflation, that describe the universe with astonishing accuracy. And yet, the ultimate origin, the very first moment, or the state before the first moment, remains elusive. Part of me wonders if it will always remain elusive, if there's something about the human condition that prevents us from fully grasping our own origins. We're finite beings, embedded in time and space, trying to understand the infinite and the eternal. We're using brains that evolved to navigate the African savanna, to track prey and avoid predators, to understand social dynamics, to survive and reproduce. Those brains are powerful, capable of abstraction and mathematics and creativity, but are they capable of fully comprehending the universe at its most fundamental level? Maybe, maybe not. We don't know until we try, until we push as far as we can, and we should try. Because even if we never reach a final answer, even if the question of what existed before the Big Bang remains forever beyond our grasp, the attempt itself is valuable. It expands our understanding. It challenges our assumptions. It forces us to think in new ways. And along the way, we discover all kinds of other things. The technologies we develop, the mathematical tools we invent, the observations we make, all of these have applications beyond cosmology. The same quantum mechanics that helps us think about the origin of the universe also gives us semiconductors and lasers and MRI machines. The same general relativity that describes the Big Bang also enables GPS satellites to work correctly. So even from a practical standpoint, even if you're not interested in abstract questions about cosmic origins, this research matters. But more than that, it matters because we're curious, because we look up at the night sky and wonder where it all came from, because we're conscious beings capable of asking questions about our own existence, and that's remarkable. It might be unique in the universe, this ability to reflect on reality, to develop theories, to test them, to build a cumulative body of knowledge that spans generations. We're the universe trying to understand itself, and that's profound. There's a passage in Carl Sagan's book, Pale Blue Dot, where he reflects on a photograph of Earth taken from the Voyager spacecraft, billions of miles away. Earth appears as a tiny speck, a pale blue dot suspended in a sunbeam. And Sagan writes about how all of human history has taken place on that dot. All the wars and triumphs and tragedies, all the kings and peasants and everyone in between. And he makes the point that this perspective should humble us, should make us recognize how small we are, how fragile our existence is. But I think there's another side to it. Yes, we're small. Yes, the universe is vast and ancient and mostly indifferent to our existence. But we're here. We're asking questions. We're figuring things out. And in that sense, we're not insignificant. We're remarkable. When I think about the question of what existed before the Big Bang, I feel a mix of emotions. There's frustration because we don't have a definitive answer. There's awe because the question itself is so immense, so profound. There's excitement because we're living in a time when we can seriously investigate these questions with sophisticated tools and theories. And there's a kind of existential vertigo because the answer, whatever it is, will fundamentally change how we see ourselves and our place in reality. If the universe came from nothing, from a quantum fluctuation in a timeless void, then existence is contingent, accidental even. We're here by chance, a statistical fluke in the vast space of possibilities. If the universe is part of an eternal multiverse, constantly spawning new universes through inflation or brain collisions or quantum branching, then we're just one tiny part of an infinite ensemble. Our universe, our Big Bang, isn't special. It's just one of countless others. If the universe is cyclical, bouncing through endless expansions and contractions, then our Big Bang is one phase in an eternal rhythm. And if time itself is an illusion, if the universe is timelessly all of its moments at once, then the question of before doesn't even make sense. Each of these possibilities has different implications for meaning, for purpose, for how we should live our lives. Or maybe they don't. Maybe the origin of the universe, however grand and mysterious, doesn't actually determine what matters to us as conscious beings living finite lives. Maybe meaning is something we create, not something we discover. Maybe the question of where we came from is separate from the question of what we should do now that we're here. But I don't think it's entirely separate. Our understanding of the cosmos shapes our worldview, our sense of place, our priorities. If we're alone in the universe, the products of a rare and precious set of circumstances, then life matters in a particular way. We're it. We're the only witnesses, the only consciousness, at least in our corner of the universe. If, on the other hand, the universe is teeming with life, or if there are countless other universes with their own conscious beings, then we're part of a much larger tapestry. We matter, but not uniquely. Both perspectives have value. Both shape how we think about ourselves. And the more we learn about the universe, the more we realize how special our existence is, even if it's not unique. The fact that the laws of physics allow for complexity, for chemistry, for biology, for consciousness, that's not guaranteed. It requires very specific values for the fundamental constants. Change the strength of the electromagnetic force, or the mass of the electron, or the cosmological constant, and you get a universe where stars can't form, or where atoms fall apart, or where everything collapses too quickly for anything interesting to happen. The universe has to be just right, balanced on a knife's edge, for us to be here asking these questions. Is that evidence of design? Some people think so. They see the fine-tuning of constants and conclude that an intelligent creator set the dials precisely to allow for life. Others see it as evidence for a multiverse, where every possible combination of constants exists somewhere, and we observe the values we do because we couldn't exist in a universe with different values. Both interpretations are consistent with the data. Science alone can't tell us which is correct, because both make the same predictions about what we should observe. This is where we venture into metaphysics, into questions that might not have empirical answers. But maybe that's okay. Maybe not every question needs to be answered by science. Maybe there's room for philosophy, for theology, for personal reflection. The question of what existed before the Big Bang might ultimately be one of those questions. We can use science to constrain the possibilities, to rule out certain answers, to develop rigorous theories that we can test. But the final answer, if there is one, might require insights that go beyond the scientific method. Or maybe not. Maybe someday we'll develop a complete theory of quantum gravity, a theory that describes the universe all the way back to the Planck time and beyond. Maybe that theory will make testable predictions, and we'll find ways to observe signatures of the pre-Big Bang state in the cosmic microwave background, or in gravitational waves, or in some other phenomenon. Maybe we'll discover that the universe is part of a multiverse, and we'll even find ways to detect the other universes, to observe their influence on ours. That might sound like science fiction, but a lot of what we consider settled science today would have sounded like science fiction 100 years ago. Think about it. General relativity predicts black holes, regions of space-time where gravity is so strong that nothing, not even light, can escape. When Einstein first published his theory, black holes were considered a mathematical curiosity, probably not real. Now, we've not only detected them indirectly through their gravitational effects, we've actually imaged one using a network of telescopes spanning the globe. We've seen the shadow of the event horizon, the point of no return. We've detected gravitational waves from black hole mergers, ripples in space-time itself propagating across the universe. 30 years ago, that would have seemed impossible. Today, it's routine. Quantum mechanics predicts entanglement, the phenomenon where two particles can be correlated in such a way that measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance and was deeply skeptical, but experiments have confirmed it. Entanglement is real, and we're now using it to develop quantum computers and quantum communication systems. What seemed like a bizarre, counterintuitive quirk of the theory is now a technological resource. So maybe the ideas we're discussing today, quantum fluctuations creating universes, eternal inflation, colliding brains, big bounces, will someday be confirmed or refuted. Maybe they'll transition from speculation to established fact. Or maybe they'll be replaced by even stranger ideas that we haven't thought of yet. The history of science is full of surprises, of theories that were once radical becoming mainstream, and of mainstream ideas being overturned by new evidence. What we need is humility, openness, and rigor. Humility to recognize that we don't have all the answers, that the universe is under no obligation to make sense to us. Openness to new ideas, even if they seem absurd at first, as long as they're consistent with the data and mathematically coherent, and rigor to test those ideas as thoroughly as possible, to follow the evidence wherever it leads, to distinguish between what we know, what we suspect, and what we're just guessing. And we need to remember that science is a process, not a collection of facts. It's a way of asking questions and finding answers, of building models and testing them, of refining our understanding over time. The picture we have today is provisional. It's the best we can do with the data and theories we have. But it will change. It always does. And that's a good thing. It means we're learning, we're progressing, we're getting closer to the truth, even if we never fully reach it. So, where does that leave us with the question of what existed before the Big Bang? Well, we have several possibilities, each with its own strengths and challenges. We have the idea that there was no before, that time itself began with the Big Bang, and asking what came before is like asking what's north of the North Pole. We have the quantum fluctuation model, where the universe emerged spontaneously from a quantum vacuum, a state of pure potentiality. We have eternal inflation, where our Big Bang is just one event in an ever-expanding multiverse. We have cyclical models, where the universe bounces through endless cycles of expansion and contraction. We have brain cosmology, where universes are higher dimensional surfaces colliding in a vast bulk. And we have more exotic ideas like the proposal that reality is fundamentally mathematical, or that time is an illusion, or that consciousness plays a role in bringing the universe into existence. None of these ideas are proven. None of them are definitive. But each offers a way of thinking about the problem, a framework for making sense of the evidence and developing testable predictions. And as we gather more data, as we refine our theories, some of these ideas will become more plausible and others will be ruled out. That's how science works. It's messy, it's uncertain, it's full of debate and disagreement. But over time, through the collective effort of thousands of scientists, we make progress. And in the meantime, we can appreciate the mystery. We can stand in awe of the fact that we live in a universe that had a beginning, that emerged from something or nothing, or perhaps from a state that transcends our usual categories of being and non-being. We can marvel at the fact that we're able to ask these questions at all, that we have the intellectual tools and the observational capabilities to probe the first moments of cosmic history. And we can find meaning in the search itself, in the journey toward understanding, even if we never reach a final destination. Because ultimately, the question of what existed before the Big Bang isn't just a scientific question, it's a human question. It's about where we come from, what our existence means, how we fit into the grand scheme of things. And those are questions that science alone can't fully answer. They require wisdom, philosophy, perhaps even spirituality. They require us to grapple not just with the mechanics of the universe, but with the meaning of our own lives. And maybe that's the real lesson here. The universe is vast, ancient, mysterious. It operates according to laws that we're still discovering, that we might never fully understand. But we're part of it. We're not separate observers looking at something external. We're made of the same atoms, subject to the same forces, governed by the same laws. The carbon in our bodies was forged in stars that lived and died billions of years ago. The oxygen we breathe was created in stellar furnaces. we're literally stardust, the universe's way of knowing itself. So when we ask what existed before the Big Bang, we're asking about our own origins, our own nature. We're asking where the story begins, how the first chapter was written. And even if we can't read that chapter, even if it's written in a language we don't fully understand, the attempt to decipher it tells us something important about who we are. It tells us that we're curious, ambitious, humble in the face of mystery, and determined to push the boundaries of knowledge. And maybe that's enough. Maybe the quest for understanding is its own reward. Maybe the beauty of the question, the profundity of the mystery, is more important than any answer we might find. Because in asking, we affirm our place in the universe. We declare that we're not content with ignorance, that we value truth and knowledge, that we're willing to confront the deepest, hardest questions about existence. And that in itself is remarkable. So I don't have a definitive answer to what existed before the Big Bang. I wish I did. But I have a deep appreciation for the question, for the way it challenges us, for the insights it offers into the nature of reality and our place in it. And I have hope that someday, maybe in my lifetime, maybe in the lifetimes of future generations, we'll know more, we'll have better theories, better data, a clearer picture. And even if we never have the complete answer, even if the ultimate truth remains just out of reach, the journey will have been worthwhile. Because in seeking to understand the universe, we come to understand ourselves. And that, I think, is what makes us human. Now, let's move on to another theory for you to reflect on. I've been thinking a lot about time lately, and the more I think about it, the more I realize that what we call time, this thing we take for granted every single day, every single moment of our lives, might not actually be what we think it is at all. It's strange, isn't it, how something so fundamental to our experience, something we use to organize everything we do, every thought we have, every plan we make, might actually be, well, not quite real in the way we imagine it. And I mean, that sounds absurd at first, right? Because time is everywhere. It's in the ticking of the clock on your wall. It's in the aging of your body. It's in the memories you have of yesterday and the plans you're making for tomorrow. Time seems to be the most obvious, the most undeniable thing in the universe. But here's the thing. Here's what keeps me up at night thinking about this. What if all of that experience of time flowing, of moments passing, of the future becoming the present, becoming the past, what if it's all a kind of trick, an illusion created by the way our minds process the universe? What if time, as we experience it, as we feel it in our bones, doesn't actually exist in the fundamental fabric of reality? Now, I know what you're thinking. You're thinking, that's crazy, right? Time obviously exists. I can measure it. I can feel it passing. Every second of my life proves that time is real. And you know what? You're absolutely right to think that, because our experience of time is so powerful, so immediate, so undeniable, that questioning it feels almost absurd. When you wake up in the morning, you remember going to sleep the night before. When you look at a clock, you see the seconds ticking away. When you think about your childhood, you absolutely know that those events happened in the past, that they're gone, that they exist only as memories now. The flow of time from past to future seems as real as the ground beneath your feet. But here's where things start to get interesting. And this is where physics, real physics, not science fiction but actual scientific discoveries, starts to tell us something very different, something that challenges everything we think we know about the nature of time. You see, when you really start to dig into what time is, when you look at what physicists have discovered over the last century or so, you find that time isn't at all what common sense tells us it should be. It's not this universal river that flows at the same rate for everyone and everything. It's not this absolute backdrop against which events occur. It turns out that time is flexible, it's relative, it's intertwined with space in ways that seem impossible and most unsettling of all. When you look at the deepest levels of reality, when you peer into the fundamental laws that govern the universe, time seems to disappear altogether, not just slow down or speed up, but actually vanish from the equations. And that's not just counterintuitive, that's shocking. That suggests that maybe, just maybe, time as we experience it is something our brains construct, a useful fiction that helps us navigate reality but doesn't actually correspond to anything fundamental in the universe itself. Let me start with something more familiar though, because I think to really understand how time might be an illusion, we need to first understand what we think time is, what our intuitions tell us, and why those intuitions are so powerful. When you think about time in your everyday life, what you're probably thinking about is what philosophers call the common sense view of time, or what physicists used to call Newtonian absolute time. This is the idea that time is like a river, flowing steadily from the past toward the future, and that this river flows at exactly the same rate everywhere in the universe. So if you're sitting here reading this and someone else is on the other side of the planet, or even on Mars, you both exist in the same now, the same present moment, and that moment is moving forward at the same steady pace for both of you. Yesterday is equally in the past for everyone, tomorrow is equally in the future, and right now, this very second, is happening simultaneously throughout the entire universe. That's the intuitive picture, and it seems so obviously true that for most of human history, nobody even questioned it. And there's good reason why this view feels so right, because in our everyday experience, it works perfectly. If you and I synchronize our watches, and then you go to the store and come back an hour later, both of our watches will still show the same time, give or take a few seconds. If I ask you what year it is, you'll give me the same answer I would give. We share a common timeline, a common past, and we're all moving together into a common future. Time seems to be this universal framework that everything exists within, this stage upon which the drama of the universe unfolds. Isaac Newton, the guy who figured out gravity and motion and so much else, he believed this absolutely. He thought time was absolute, that it flowed equably without relation to anything external, as he put it. Time, in Newton's view, was something fundamental, something that would exist even if there was nothing in the universe, no matter, no energy, no motion, just empty space, and absolute time ticking away into eternity. But here's the thing, and this is where our story really begins. Newton was wrong. Not about everything. I mean, his physics works brilliantly for everyday situations, for throwing baseballs and launching rockets and predicting planetary orbits. But about time, about the fundamental nature of time, he was wrong in a deep and profound way. And the person who showed us just how wrong he was, well, that was Albert Einstein. Now, I know everyone talks about Einstein. He's become this iconic figure, this symbol of genius. And sometimes that makes it hard to appreciate just how revolutionary his ideas actually were. But when it comes to time, Einstein didn't just refine our understanding or make some minor corrections to the old view. He completely upended it. He showed that time is not absolute, not universal, not the same for everyone. He showed that time is relative, that it depends on how fast you're moving and how strong the gravitational field is around you. And most importantly, he showed that time and space are not separate things, but are woven together into a single unified fabric called space-time. Let me try to explain what that actually means, because it's weird, it's really weird, and it takes some time to wrap your head around. Einstein's first major breakthrough, which came in 1905, when he was just 26 years old and working as a clerk in a patent office, was what we now call special relativity. And what special relativity tells us is that time is not absolute. Different observers, moving at different speeds, will experience time differently. If you're sitting still and I'm moving very fast, maybe close to the speed of light, then time will literally pass more slowly for me than it does for you. This isn't just an appearance or a trick of perception, it's real. If I get on a spaceship and fly away from Earth at, say, 90% of the speed of light, and I travel for what feels to me like 1 year, then when I come back to Earth, I'll find that much more time has passed here. Maybe 5 years, maybe 10 years, depending on exactly how fast I was going. This is called time dilation, and it's not speculation or philosophy. It's been tested and confirmed thousands of times in particle accelerators and with atomic clocks on airplanes and satellites. Time really does pass at different rates depending on your motion. Now, you might be thinking, okay, that's strange, but how does that make time an illusion? After all, time is still passing, just at different rates for different observers. And you're right, special relativity doesn't immediately suggest that time is an illusion, but it does something important. It breaks that notion of absolute universal time. It tells us that there's no such thing as a universal now that extends throughout the entire universe. When you say, what's happening on Mars right now, that question actually doesn't have a single definitive answer. It depends on your frame of reference, on how fast you're moving. An observer moving at a different speed would have a different answer to the question of what now means on Mars. The present moment, it turns out, is not an objective feature of the universe. It's relative. It's observer dependent. And that's the first crack in our intuitive understanding of time, the first hint that maybe time isn't quite what we think it is. But Einstein didn't stop there. 10 years later, in 1915, he published his theory of general relativity, and this is where things get even stranger. General relativity extends special relativity to include gravity, and what Einstein realized is that gravity isn't actually a force in the traditional sense. It's not something that reaches out across space and pulls objects together. Instead, gravity is the curvature of space-time itself. Mass and energy curve the fabric of space-time, and objects moving through that curved space-time follow paths that we interpret as gravitational attraction. A planet orbiting a star, for instance, is just following the straightest possible path through the curved space-time created by the star's mass. And here's the crucial part for our discussion. When space-time is curved, time itself is affected. Time passes more slowly in stronger gravitational fields. If you're standing at sea level and I'm standing on top of a mountain, time is passing slightly faster for me than it is for you because I'm farther from the Earth's mass and the gravitational field is slightly weaker up here. Again, this has been measured. Atomic clocks at different altitudes tick at different rates, and GPS satellites have to account for this effect, or they'd give you completely wrong positions. So now we have a picture where time is not only relative to motion, but also relative to gravity. Time is flexible, stretchy, variable depending on where you are and how fast you're going. But there's something even more profound in Einstein's equations, something that really challenges our intuitive understanding of time. In general relativity, space and time are not separate things. They're unified into space-time, a four-dimensional fabric where the three dimensions of space and the one dimension of time are all mixed together. And in this four-dimensional space-time, the distinction between past, present, and future is not what we think it is. Einstein himself, in a letter to the family of his friend Michel Besso after Besso died, wrote something extraordinary. He wrote, "Now he has departed from this strange world a little ahead of me. That means nothing. People like us who believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion." Only a stubbornly persistent illusion. Think about that for a moment. One of the greatest physicists who ever lived, the man who revolutionized our understanding of space, time, and gravity, is saying that the distinction between past, present, and future, the very essence of what we call time, is an illusion. What Einstein is getting at here, what his equations seem to suggest, is something called the block universe view of time, or eternalism. This is the idea that the past, present, and future all exist equally, that they're all equally real, and that the flow of time, this feeling we have of moving from the past through the present into the future, is not a feature of the universe itself, but rather something about how we perceive the universe. Imagine, if you will, a book. The book has many pages, and each page represents a moment in time. Now, all of those pages exist simultaneously. The first page, the middle pages, the last page, they're all there in the book at the same time. When you read the book, you experience it sequentially, one page after another, and you have this sense of moving through the story. But from the perspective of the book itself, from a perspective outside of your reading experience, all the pages exist together. That's the block universe. All of space-time, all of history, from the Big Bang to the end of the universe, exists as a single, unchanging, four-dimensional structure. Your birth, your childhood, this moment right now, your eventual death, they all exist together in the block universe. The passage of time, the feeling that the present moment is somehow special, somehow more real than the past or the future, that's just your consciousness moving through the block, experiencing one slice at a time. Now, I know that sounds bizarre, and maybe it sounds deeply unsettling. If the block universe is true, then in some sense, everything that will ever happen to you has already happened, already exists out there in the structure of space-time. Your future is as fixed and real as your past. And that raises all sorts of questions about free will and choice, and whether the future is predetermined, questions we'll come back to later. But for now, what I want you to see is that this view of time, which comes directly from Einstein's equations, from the mathematics of general relativity suggests that time as we experience it, time as a flowing river carrying us from past to future, is not built into the fundamental structure of reality. It's something else, something about our perspective, our consciousness, our way of experiencing the world. But wait, there's more. Because as strange as Einstein's relativity is, it's not even the deepest level of physics. When we look at the quantum world, the world of atoms and electrons and fundamental particles, things get even weirder, and time becomes even more mysterious. Quantum mechanics, which is the physics of the very small, has its own strange relationship with time. In the equations of quantum mechanics, time appears in a fundamentally different way than it does in relativity. In quantum theory, time is what we call a parameter rather than an observable. What that means is that you can't measure time in the same way you can measure position or momentum or energy. Time is the backdrop against which quantum events happen, but it's not something that quantum systems have a value for in the same way they have a value for other properties. And this creates a deep tension between quantum mechanics and general relativity, because in relativity, time is woven into space-time and is affected by matter and energy, while in quantum mechanics, time is external, absolute in a weird way, not part of the quantum description of reality. And this tension, this incompatibility between quantum mechanics and general relativity, has led physicists to search for a deeper theory, a theory of quantum gravity, that would unite these two great pillars of modern physics. And here's where things get really interesting for our question about time, because when physicists try to create quantum theories of gravity, time has a tendency to disappear from the equations altogether. The most famous example of this is something called the Wheeler-DeWitt equation, which is an attempt to apply quantum mechanics to the entire universe, to the geometry of space-time itself. And when you write down this equation, when you try to describe the quantum state of the universe as a whole, time doesn't appear in the equation at all. It's not that time is flowing differently or that it's relative or that it's flexible. It's that time is simply not there in the fundamental description of reality. The universe, at its deepest level, at the level of quantum gravity, appears to be timeless, frozen, eternal. Now, this is called the problem of time in quantum gravity, and it's one of the deepest unsolved problems in all of physics. How can the universe be timeless at the fundamental level, and yet we experience time so vividly in our everyday lives? How does time emerge from a timeless reality? And there are various proposals, various ideas about how this might work, but none of them are fully satisfactory yet. None of them are proven. But what they all suggest, what this whole line of investigation points toward, is that time as we know it is not fundamental. It's not built into the deepest level of reality. Instead, time is something that emerges, that appears when you look at the universe from a particular perspective or at a particular scale, but which isn't there in the underlying structure of things. Let me try another approach to this, another way of thinking about how time might be an illusion, or at least not what we think it is. Think about the arrow of time, the fact that time seems to have a direction. We remember the past, but not the future. Eggs break, but don't unbreak. Coffee cools down, but doesn't spontaneously heat back up. There's an asymmetry to time, a clear distinction between past and future. But here's the strange thing. The fundamental laws of physics don't have this asymmetry. If you look at the equations that govern the behavior of particles, whether it's Newton's laws or Einstein's equations or the Schrödinger equation in quantum mechanics, these equations work just as well forward in time as backward in time. You can run the movie of physics forward or backward, and the fundamental laws don't care. They're time symmetric. So where does the arrow of time come from? Why does time have a direction if the fundamental laws don't distinguish between past and future? The answer, or at least the best answer we have, comes from thermodynamics, from the study of heat and entropy. The second law of thermodynamics says that entropy, which is roughly a measure of disorder, or the number of possible microscopic arrangements of a system, always increases over time in a closed system. And this increase in entropy is what gives time its arrow. It's why things run down, why structures decay, why eggs break and don't unbreak. But here's the crucial point. Entropy is not a fundamental property of individual particles. It's a statistical property of large collections of particles. When you have billions and billions of atoms or molecules, the chances that they'll spontaneously arrange themselves into a lower entropy state, that a broken egg would spontaneously reassemble itself, are astronomically small. Not impossible, the fundamental laws don't forbid it, but so unlikely that it never happens in practice. So the arrow of time, the directionality of time that we experience, emerges from statistics, from the behavior of large numbers of particles, not from the fundamental laws themselves. And this is another hint that time as we experience it is not fundamental. The flow of time, the arrow of time pointing from past to future, is something that emerges from the collective behavior of many particles, not something built into the basic structure of reality. An individual particle, an individual electron or quark, doesn't experience time passing in the way we do. It doesn't distinguish between past and future. It just exists in accordance with timeless laws. Time, in this view, is a statistical phenomenon, an emergent property that appears when you have complex systems with many parts, but which isn't there at the most basic level. And if time emerges, rather than being fundamental, if it appears only at certain scales or from certain perspectives, then in what sense is it real? In what sense is it more than an illusion, a useful way of organizing our experience, but not a genuine feature of ultimate reality? Now, let's think about this from another angle, from the perspective of consciousness and perception. When you experience time, when you feel time passing, what's actually happening? What is it that gives you this sense of duration, of moments flowing from one to the next? Neuroscientists and psychologists have studied this extensively, and what they've found is that our perception of time is a construction, a model that our brains create from sensory input and memory and internal processes. The sense of the present moment, for instance, is not actually instantaneous. It's not a single mathematical point in time. Instead, what we call now is a kind of averaging over a short period, maybe a few hundred milliseconds, during which our brains integrate information and construct a coherent experience. You don't experience reality as a series of disconnected instants. You experience it as a flowing, continuous present, and that continuity is something your brain creates. And our sense of time can be distorted in all sorts of ways. When you're in danger, time seems to slow down. When you're having fun, time flies. When you're bored, minutes feel like hours. When you're asleep, hours pass without any subjective experience of duration at all. The rate at which you experience time depends on your psychological state, on what you're paying attention to, on how much new information you're processing. Children experience time more slowly than adults, probably because everything is new to them, because they're forming more memories per unit of actual time. As we age, time seems to speed up. Years fly by faster and faster, perhaps because we're having fewer novel experiences, because we're laying down fewer distinct memories. All of this suggests that time as we experience it is not an objective feature of the external world, but a construct of our minds, a way our brains organize information and create a sense of narrative continuity. And then there's memory. Our entire sense of the past, our conviction that there was a yesterday that really happened, depends on memory. But memories are not like photographs, not accurate records of past events. They're reconstructions, constantly updated and modified by our present state and beliefs. Every time you remember something, you're not accessing a stored recording. You're rebuilding that memory from pieces, and in the process, you can change it, distort it, even create false memories that never happened. So the past, as you experience it, as you remember it, is not a fixed thing. It's a story your brain tells you, a story that can change. And if the past is not fixed in your experience, if it's constantly being rewritten, then what does it mean to say that the past is real? What does it mean to say that time is flowing from a definite past through the present into the future? Some philosophers and physicists have taken these ideas even further. They've argued that consciousness itself, the very fact that we're aware, that we have subjective experiences, is intimately connected to our sense of time. Without consciousness, they argue, there would be no distinction between past, present, and future. There would just be the timeless structure of the universe, the block universe, sitting there in four-dimensional space-time. It's consciousness that creates the flow of time, that selects a particular sequence through the block universe and experiences it as a temporal flow. In this view, time doesn't exist independently of conscious observers. Time is something that emerges from the interaction between the physical universe and conscious beings who perceive that universe in a particular way. And if that's true, if time requires consciousness to exist, then time really is an illusion in a sense, not a fundamental feature of the universe, but a feature of how certain systems like us, interact with and perceive the universe. Now, I want to be careful here because I don't want to give you the impression that all physicists agree about this or that we have definitive answers. We don't. The nature of time is still one of the most debated questions in physics and philosophy. There are physicists who believe that time is fundamental, that it's not an illusion, that the block universe view is wrong, and that the flow of time is real and built into the structure of reality. There are different approaches to quantum gravity, like loop quantum gravity or string theory, that treat time in different ways. Some theories suggest that time is fundamental, others that it's emergent, and others still that it's a more complicated mixture of both. The honest truth is that we don't fully understand what time is, and we certainly don't have a complete theory of quantum gravity that would give us a definitive answer. But what we do know, what the evidence does tell us, is that time is not what our intuitions suggest. It's not absolute, it's not universal, it's not independent of space or motion or gravity. It's flexible, relative, intertwined with the fabric of space-time in ways that completely contradict our everyday experience. And at the deepest levels of physics, when we try to describe the quantum nature of the universe itself, time seems to disappear from the fundamental equations. So even if we can't say definitively that time is an illusion, we can say that time is deeply mysterious, that it's not at all what it seems, and that there's good reason to think that time as we experience it is an emergent phenomenon, something that appears from a particular perspective, but which isn't built into the deepest structure of reality. Let me come at this from yet another direction, because I think to really understand this, you need to see it from multiple angles. Think about the present moment, the now that you're experiencing right this second. What is it? When is it? If you try to pin it down to say exactly when now is, you run into problems. Is the present moment this second, this millisecond, this nanosecond? How thin is the present? And as soon as you start thinking about it, as soon as you become aware of now, it's already the past. The present is constantly slipping away, constantly becoming the past, and the future is constantly becoming the present. The present moment seems to be a knife edge between past and future, infinitesimally thin. And yet it's also the only time we ever actually experience. We don't experience the past, we remember it. We don't experience the future, we anticipate it. All we ever have is this fleeting, indefinable present. But in the block universe view, there is no special present moment. Every moment in time exists equally in the four-dimensional structure of space-time. Your experience of this present moment is just your particular location in the block universe, the particular slice of space-time that your consciousness is currently experiencing. But there's nothing special about this slice from the perspective of the universe itself. It's just one moment among all moments, all equally real, all existing together in the timeless structure of space-time. The present, in this view, is like a location in space, just as here is special to you because you're located here, but not special from the perspective of the universe as a whole. Now is special to you because you're experiencing it now, but not special from the perspective of the universe as a whole. The present is subjective, observer-dependent, not an objective feature of reality. And this connects to something interesting that happened in the early 20th century, a famous debate between Einstein and the philosopher Henri Bergson. Bergson believed deeply in the reality of time, in the flow of duration, as he called it. He thought that time as we experience it, with its sense of flow and becoming, was fundamental to reality. Einstein, on the other hand, believed that time as described by physics, relative and intertwined with space, was the true nature of time, and that our subjective experience of temporal flow was, well, not quite real, not built into the structure of the universe. They had a public confrontation in 1922, and it's fair to say that Einstein won, at least in the scientific community. But Bergson raised important questions. If time as physics describes it is so different from time as we experience it, if the flowing dynamic time of our consciousness has no counterpart in the timeless equations of physics, then how do we reconcile these two pictures? How do we explain the fact that we experience something that doesn't seem to exist at the fundamental level of reality? This is sometimes called the hard problem of time, in analogy with the hard problem of consciousness. The hard problem of consciousness is the question of why we have subjective experiences at all, why there's something it's like to be us, why we're not just unconscious information processing machines. The hard problem of time is similar. Why do we experience time as flowing? Why does the present feel special? Why do we have this sense of becoming and change when the underlying physics seems to describe a static, timeless, or at best time-symmetric reality? And just as with consciousness, there's no agreed-upon answer. Some people think that the experience of time will ultimately be explained by neuroscience, by understanding how our brains process information and create the illusion of temporal flow. Others think that there's something about time that we're missing, some aspect of reality that our current physics doesn't capture, that will explain why time really does flow after all. Let me tell you about another fascinating aspect of this, something that comes from quantum mechanics and the nature of causality. In classical physics, in Newton's world or even Einstein's world, causality is clear. Events in the past cause events in the future. You can't have an effect before its cause. Time's arrow and causality go hand in hand. But in quantum mechanics, things are not so clear. Quantum mechanics allows for strange phenomena like entanglement, where two particles can be correlated in ways that seem to involve instantaneous influences across space. If you measure one entangled particle and find it in a particular state, you instantly know what state the other particle is in, even if it's on the other side of the galaxy. This doesn't violate relativity. It doesn't allow faster than light communication, but it does suggest that the quantum world has non-local connections that don't fit neatly into our usual picture of events being connected by chains of causes and effects propagating through time. And there are even more exotic quantum phenomena that seem to play with time itself. Wheeler's delayed choice experiment, for instance, seems to suggest that a choice you make now can affect what happened in the past. Now, that's not quite right. That's a misleading way to describe it. But the experiment does show that the quantum world doesn't have a definite state until it's measured. And what you choose to measure can affect what the past state of the system was in a certain sense. It's not time travel, it's not causality violation. But it does suggest that the quantum world's relationship to time is even stranger than what we see in relativity. Past and future, cause and effect, these distinctions seem to blur at the quantum level in ways that challenge our intuitive understanding of how time works. And then there are theories, speculative but taken seriously by some physicists, that suggest time might not be continuous at all. Maybe time is made up of discrete moments, individual frames like a movie, separated by some fundamental minimum interval, perhaps the Planck time, which is about 10 to the minus 43 seconds. If time is discrete rather than continuous, if it's made up of individual ticks rather than flowing smoothly, then in what sense is it flowing at all? It would be more like a series of static snapshots with no flow between them, just one snapshot, then the next, then the next. And again, that challenges our experience of time as a smooth, continuous flow. It suggests that the flow is something our brains create, a way of stitching together discrete moments into a sense of continuous experience. I want to talk now about some alternative theories of time, approaches that physicists and philosophers have developed that might help us understand how time could be an illusion, or at least not what it seems. One of the most interesting is the idea that time is thermodynamic, that time is fundamentally about entropy and the increase of disorder. In this view, championed by physicists like Carlo Rovelli, time doesn't exist at the fundamental level of reality. The fundamental laws of physics are timeless or time-symmetric. But when you have systems with many particles, when you take into account the fact that we're always dealing with incomplete information about the exact state of every particle, then entropy becomes important and an arrow of time emerges. Time, in this view, is a macroscopic phenomenon, something that appears, when you zoom out from the microscopic timeless laws and look at the large-scale statistical behavior of matter and energy, Ravelli has this beautiful way of putting it. He says that time is like heat. At the microscopic level, there's no such thing as heat. Heat is not a fundamental property of individual atoms. Instead, heat is the random kinetic energy of many atoms moving around. When you zoom out and look at a gas or a liquid, you can describe it with a temperature which is related to the average kinetic energy of the particles. Temperature is a macroscopic, emergent property. And time, Ravelli argues, is similar. At the microscopic level, in the fundamental laws, there's no time, or time is so different from what we experience that it's barely recognizable. But when you zoom out, when you look at complex systems with many particles, an arrow of time emerges from the increase in entropy, and we perceive this as the flow of time. Time is not fundamental. It's a way of describing our interaction with the universe from a macroscopic, information-limited perspective. And this connects to another idea that's been gaining traction in physics, the idea that information might be more fundamental than matter or energy or even space-time. Some physicists think that the universe is, at its deepest level, made of information, and that space, time, matter, and energy are all emergent properties that arise from the way information is organized and processed. In this view, time would be a particular way that information changes or that we access information about the universe. The past is the information we have stored in memories and records. The future is the information we don't yet have. The present is the information we're currently processing. And the flow of time is the updating of our information about the state of the universe. This is a radical view, and it's still very much speculative, but it's being taken seriously by physicists working on quantum information theory and quantum gravity. Let's also consider the philosophical implications of all this, because if time is an illusion, if the flow of time is not built into the fundamental structure of reality, then what does that mean for us, for our lives, for the way we understand ourselves? One of the most troubling implications is about free will. If the block universe is correct, if all of time exists at once, if the future is already out there in the structure of space-time just as much as the past is, then it seems like the future is fixed. Everything that will happen has, in a sense, already happened. It exists in the block universe. So do we have any real choice? Can we actually affect the future, or are we just experiencing predetermined events that already exist in the four-dimensional structure of space-time? Now, this is a deep and difficult question, and there's a lot of debate about it. Some philosophers argue that even in a block universe, free will is still possible. They say that free will doesn't require an open, undetermined future. It just requires that our choices are not determined by anything external to us, that we're the authors of our own actions, even if those actions exist timelessly in the block universe. Other philosophers think that the block universe really does undermine free will, that if the future is already fixed, then we're just experiencing a predetermined sequence of events, and our sense of making choices is an illusion. And others still think that quantum mechanics might save free will, that the inherent randomness or indeterminacy in quantum processes might allow for genuine openness in the future, even if we can't predict or control that openness. But there's something interesting here, something worth thinking about. Even if the block universe is true, even if all of time exists at once, we don't experience it that way. We experience time as flowing. We experience ourselves as making choices, as affecting the future through our actions. And maybe that's enough. Maybe what matters is not whether time is ultimately real or illusory at the fundamental level of physics, but how we experience it, how we live our lives within the experience of temporal flow. After all, even if color is ultimately just electromagnetic waves of different frequencies, even if there's no redness in the light itself, but only in our perception, that doesn't make the experience of seeing red any less real for us. Similarly, even if time is ultimately an illusion, even if it's not fundamental to the universe, that doesn't make our experience of time any less vivid, any less important, any less meaningful. And there's something profound in that, I think. One of the lessons from all of this, from Einstein's relativity to quantum mechanics to modern theories of quantum gravity, is that the universe is under no obligation to match our intuitions. Reality doesn't have to make sense to us. It doesn't have to fit into categories that feel natural or comfortable. The universe is what it is, and our job as conscious beings trying to understand it is to follow the evidence wherever it leads, even if it takes us to places that seem strange or counterintuitive or even impossible. And time, it turns out, is one of those places. Time is not what it seems. It's not what our everyday experience tells us it should be. It's weirder, more subtle, more mysterious than we ever imagined. Let me tell you about some other traditions and perspectives on time, because Western physics isn't the only way humans have thought about this question. In Buddhist philosophy, for instance, there's a concept that's remarkably similar to some of what modern physics is telling us. Buddhism teaches that the self is an illusion, that there's no permanent, unchanging I that persists through time. Instead, what we call the self is a constantly changing process, a series of moments of consciousness arising and passing away. And time, in Buddhist thought, is intimately connected to this. The past is gone, the future hasn't come, and the present is so brief that by the time you become aware of it, it's already past. The present moment, in a deep sense, doesn't exist as a thing that endures. There are only changes, processes, transformations. And if you really see this, if you really understand that the self and time are both empty of inherent existence, then you can be liberated from suffering, from the anxiety and grasping that comes from trying to hold on to a self and a time that aren't really there. Now, I'm not saying that Buddhist philosophy and modern physics are saying exactly the same thing. They come from very different traditions, very different ways of investigating reality. But there's an interesting convergence, a similarity in the conclusion that time, as we ordinarily conceive it, is not ultimately real. And this shows up in other traditions too. Some interpretations of mystical experiences in various religions describe a sense of timelessness, a feeling of being outside of time, where past, present, and future collapse into an eternal now. Whether these experiences tell us something deep about the nature of reality or are just interesting states of consciousness, I don't know, but they do suggest that the human mind is capable of experiencing something other than the usual flow of time, that our normal temporal experience is not the only possible way of relating to the world. And in Western philosophy too, there have been thinkers who question the reality of time. The ancient Greek philosopher Parmenides argued that change is impossible, that reality is a single, unchanging, eternal being, and that the appearance of change and time is an illusion. Most philosophers thought Parmenides was wrong, but his arguments were serious enough that people had to grapple with them. And in the 20th century, the philosopher J.M.E. McTaggart famously argued that time is unreal based on what he saw as contradictions in the way we think about past, present, and future. While most philosophers don't accept McTaggart's argument, it sparked a huge literature on the philosophy of time, on what it means for something to be in the past or present or future, on whether time really flows or whether that's an illusion of perspective. So this question, this deep question about the reality of time, is not just a scientific question. It's a philosophical question, a psychological question, maybe even a spiritual question. It touches on everything from the fundamental laws of physics to the nature of consciousness to how we should live our lives. And that's part of what makes it so fascinating, so endlessly interesting. It's not just an abstract puzzle. It's a question about the deepest nature of our existence, about what it means to be a conscious being experiencing a reality that may not be quite what it seems. Now, let me come back to some more recent developments in physics, because there have been some fascinating new ideas about time in the last couple of decades. One of the most interesting comes from an approach to quantum gravity called causal set theory. In this approach, space-time is not continuous, but is made up of discrete elements, individual events that are connected by causal relationships. It's like space-time is built out of a huge network of points, and what determines the structure of space-time is which points can influence which other points. Time, in this view, emerges from the causal structure, from the network of influences between events. There's no separate thing called time. There's just the pattern of causality, and time is a way of describing that pattern. And interestingly, in causal set theory, you can have different orderings of events depending on how you traverse the network. Time is not absolute, it's not even unique. It's a way of organizing events based on causality, and there may be multiple ways to do that. Another fascinating approach comes from the idea of emergent time in various quantum gravity theories. The idea here is that time, and possibly space too, are not fundamental but emerge from something deeper, something more abstract. Maybe reality, at its deepest level, is describable in terms of abstract quantum states that have no spatial or temporal properties at all. Space-time, as we know it, with its 3 dimensions of space and 1 dimension of time, would then be something that emerges when you look at these quantum states from a particular perspective, or when the universe is in a particular regime, maybe at energies well below the Planck scale where quantum gravity effects are negligible. It's similar to how the smooth surface of a body of water emerges from the collective behavior of countless molecules. Up close, at the molecular level, there's no smooth surface. There are just individual water molecules bouncing around. But zoom out and a surface appears. Similarly, zoom out from the quantum gravity scale and space-time appears, along with time as we experience it. And this connects to another idea that's been influential in recent physics, holography. The holographic principle, which comes from studying black holes and string theory, suggests that all the information in a volume of space can be encoded on the boundary of that volume, kind of like how a 3-dimensional image can be encoded in a 2-dimensional hologram. If this principle is correct, and there's good reason to think it might be, then the 3-dimensional space we experience is in some sense an illusion, a projection from a lower dimensional boundary. And if space is emergent in this way, if it's not fundamental, then probably time is emergent too. The holographic principle doesn't give us a complete picture of how time emerges, but it strongly suggests that space-time as we know it is not the deepest level of reality, that there's something more fundamental from which space-time, including time, emerges. There's also been interesting work on something called the thermal time hypothesis, which was developed by physicists trying to understand how time relates to thermodynamics and quantum mechanics. The idea is that time is defined by thermodynamic processes, by the flow of entropy. In a system in thermal equilibrium, where entropy is at a maximum and not changing, there would be no time in this view. Time emerges only in systems that are out of equilibrium, where entropy can increase. This is a technical idea with a lot of mathematical details, but the basic insight is similar to what we talked about earlier. Time is not fundamental, but emerges from thermodynamic considerations, from the macroscopic behavior of systems with many degrees of freedom. And I want to mention one more approach that I find particularly intriguing, which comes from the physicist Lee Smolin and a few others who argue that time is real, that it's fundamental, and that the block universe view is wrong. Smolin argues that physics has taken a wrong turn in treating time as just another dimension like space, in describing the universe with timeless equations that treat all of time as existing at once. Instead, he proposes that time is fundamentally different from space, that the present moment is objectively real and special, and that the future genuinely doesn't exist yet, doesn't become real until it happens. He calls this view temporal naturalism, and he's developed it into a full philosophical and scientific framework. Now, Smolin's view is controversial and not accepted by most physicists, but it's worth mentioning because it shows that there are serious thinkers who resist the idea that time is an illusion, who think that our intuitive sense of time as flowing is actually correct, and that physics needs to be reformulated to accommodate this. So where does all of this leave us? What are we to make of the idea that time might be an illusion? Well, I think the honest answer is that we don't know for sure. We don't have a complete theory of quantum gravity yet. We don't fully understand how to reconcile quantum mechanics with general relativity. We don't know whether time is fundamental or emergent, whether the block universe is correct or whether time really flows, whether the present moment is objectively special or just a subjective experience. These are open questions, questions that physicists and philosophers are actively working on, questions that may not be fully resolved for decades or even longer. But what we do know is that time is not what common sense tells us it is. It's not absolute, not universal, not independent of space and motion and gravity. Our intuitive picture of time as a flowing river that carries all of us along at the same rate, that's demonstrably wrong. Time is relative, flexible, observer-dependent, and at the deepest levels of physics, time seems to disappear or at least transform into something so different from our everyday experience that calling it time almost seems misleading. And I think there's something beautiful in this uncertainty, in this mystery. We live our lives immersed in time. We plan for the future. We remember the past. We experience the present moment slipping away, instant by instant. Time structures our entire existence. And yet, when we look closely, when we probe deeply into the nature of reality, time becomes elusive, mysterious, perhaps even illusory. It's like we're living in a grand magic trick, experiencing something that feels absolutely real, absolutely undeniable, and yet which may not exist in the way we think it does at the fundamental level of the universe. And that's humbling. It reminds us that reality is stranger than we can imagine, that the universe doesn't owe us explanations that make intuitive sense, that some of the deepest truths about existence may be forever counterintuitive, forever at odds with our everyday experience. But there's another side to this, something that's easy to miss in all the physics and philosophy. Even if time is an illusion at the fundamental level, even if the block universe is true and all of time exists at once in some four-dimensional structure that doesn't change how we live, we still experience time as flowing. We still make choices, form memories, anticipate the future, live our lives in what feels like a dynamic, unfolding present. And that experience is real. It's real for us. The illusion, if it is an illusion, is a remarkably powerful and consistent one. It's not like we can just decide to experience time differently because we've learned that the physics of time is strange. We're embedded in our temporal experience. It's part of what we are as conscious beings. And maybe that's the key insight here. Maybe the question isn't really whether time is real or illusory at some abstract fundamental level. Maybe the question is about levels of description, about the fact that the universe can be described in different ways at different scales, and all of these descriptions can be valid, can be real in their own contexts. At the level of fundamental physics, at the Planck scale, or in the equations of quantum gravity, time might be absent or radically different from what we experience. At the level of everyday life, of human experience, of biology and psychology and society, time is absolutely real, absolutely fundamental to how we understand ourselves and the world. And both of these descriptions can be true simultaneously. They're descriptions of the same reality at different scales, different perspectives. The time of physics and the time of experience are not the same thing, and that's okay. That's not a contradiction. It's just a reflection of the richness and complexity of reality. You know, Einstein once said something else about time that I find really poignant. He said that for those of us who believe in physics, the separation between past, present, and future is an illusion. But he also acknowledged that this was a stubborn illusion, one that we can't shake, one that shapes our entire lives. And I think he's right. Even Einstein, who understood the relativity of time better than almost anyone, still lived his life as if time flowed, as if the present moment was special, as if the past was gone and the future was yet to come. He couldn't help it. None of us can. We're built to experience time this way. Our brains, our nervous systems, our very consciousness is structured around the flow of time. And that's not a failure of understanding. That's just the nature of being a human being, a conscious creature embedded in a universe that's far stranger and more subtle than it appears. So what does all of this mean for how we should think about our lives, about mortality, about the passage of time that seems to accelerate as we age? If time is an illusion, does that mean death is an illusion too? Does it mean that all moments of our lives exist eternally in the block universe? That in some sense we never truly die because every moment of our existence is frozen forever in the four-dimensional structure of space-time? Maybe. The block universe view does suggest something like that. If all of time exists at once, then every moment of your life, from birth to death, exists permanently in the structure of space-time. In that sense, you're immortal. Not in the sense of living forever into the future, but in the sense of existing timelessly in all the moments of your life. Your death is no more final than your birth, because both are just locations in the block universe. Both exist equally. Both are permanent features of the four-dimensional structure of reality. But I'm not sure how much comfort that provides, honestly, because even if all moments of our lives exist eternally, in some abstract sense, We don't experience it that way. We experience a flow from birth toward death, a progressive narrowing of possibilities, an accumulation of past and a shrinking future. And that experience is what matters to us. The fear of death, the sense of time running out, the feeling of moments slipping away. These are real experiences, real emotions, real aspects of what it means to be human. Telling someone that time is an illusion doesn't make them any less afraid of dying. It doesn't make the loss of a loved one any less painful. Because the illusion, if it is an illusion, is part of the texture of conscious experience. It's not something we can step outside of. And yet there's something valuable in this perspective, something that might help us live better, appreciate more. If time is an illusion, if all moments exist equally in some sense, then maybe we should pay more attention to each moment. Maybe we should be less obsessed with rushing toward the future, with always planning, always anticipating, always waiting for the next thing. Maybe we should spend more time in the present, experiencing it fully, recognizing that this moment right now is as real and as valuable as any moment in the future or the past. There's a way in which understanding that time might be an illusion could make us more present, more aware, more conscious of the miracle of existence. And there's also something humbling in all of this. The fact that we don't understand time, that our experience of it is so different from what physics tells us about it, reminds us that we don't have all the answers. We're finite beings trying to understand an infinite universe. We're creatures who experience time in one particular way, trying to understand the fundamental nature of time itself. Of course, we're going to be confused. Of course, we're going to find contradictions and mysteries and questions that seem unanswerable. But that's the adventure, isn't it? That's what makes the pursuit of knowledge worthwhile. Not knowing everything, not having all the answers, but asking the questions, following the evidence, being willing to have our intuitions challenged and our worldviews upended. I think about this sometimes, about how every human who has ever lived has experienced time in roughly the same way. Every person who has ever watched the sun rise and set, who has aged from child to adult to elder, who has remembered yesterday and planned for tomorrow, has shared this experience of temporal flow. And yet, it may be that this universal human experience doesn't correspond to anything fundamental in the structure of the universe. It's a shared illusion, a common feature of being a conscious creature with memory and anticipation, but not a feature of reality itself. And there's something both unsettling and beautiful about that. Unsettling because it means our most basic intuitions about the world are wrong. Beautiful because it means reality is far richer, far stranger, far more mysterious than we ever imagined. And maybe that's the ultimate lesson here. Reality doesn't care about our intuitions. It doesn't care about what feels right or what makes sense to us. The universe is under no obligation to be comprehensible to human minds. And yet, remarkably, we've been able to make progress. We've been able to develop theories, conduct experiments, build technologies that work, that predict and manipulate reality with extraordinary precision. We've uncovered some of the deep secrets of space and time and matter and energy, even though those secrets turn out to be far stranger than anyone anticipated. That's the power of the scientific method, of following evidence wherever it leads, of being willing to question everything, even our most basic assumptions about the nature of existence. So is time an illusion? Maybe, probably, in some sense. But what exactly that means, what the true nature of time is, how our experience of temporal flow relates to the timeless equations of fundamental physics, these are questions we're still working on. They're questions that may not have simple answers, that may require us to develop entirely new ways of thinking about reality. But that's okay. That's how knowledge progresses. Each answer opens up new questions. Each solution to a mystery reveals deeper mysteries beneath. And the mystery of time, the question of whether this fundamental dimension of our existence is real or illusory, is one of the deepest mysteries there is. It's a question that takes us to the very edge of human understanding, to the boundary between what we know and what we can perhaps never know. And standing at that boundary, looking out at the vast unknown, feeling the weight of all the things we don't understand, there's a sense of awe, of wonder, of humility. We're small creatures on a small planet, orbiting an ordinary star in an unremarkable galaxy. And yet we're able to ask these questions, to probe the nature of time itself. We're able to discover that our intuitions are wrong, that reality is stranger than we imagined, that time, this thing we take so utterly for granted, might be an illusion. And there's something profoundly human about that, about the drive to understand, to question, to push against the boundaries of knowledge, even when what we find challenges everything we thought we knew. Maybe time is an illusion, maybe it's real, but not in the way we think. Maybe the answer is something we haven't even conceived of yet, something that will require a revolution in physics as profound as Einstein's revolution a century ago. Whatever the answer turns out to be, the journey toward understanding is worthwhile, because in trying to understand time, we're trying to understand ourselves, our place in the universe, the nature of existence itself. And even if we never fully succeed, even if time remains mysterious and elusive, the attempt itself is meaningful. It's what makes us human. It's what connects us to every other human who has ever looked up at the stars and wondered, who has ever asked the big questions, who has ever dared to challenge the obvious and seek the truth beneath. So here we are, you and I, existing in what we experience as the present moment, separated from the past by memory and from the future by anticipation, living our lives as if time flows, even though the deepest laws of physics suggest it might not. And that's okay. That's beautiful even. We're experiencing a magnificent illusion, if illusion it is, one that gives structure and meaning to our existence. We're part of a universe that's far stranger than it appears, a universe where time might not be real, but where our experience of time is vivid and undeniable. And in that tension, in that gap between how things seem and how they are, we find something profound. We find mystery, we find wonder, we find the endless, fascinating, humbling adventure of trying to understand a reality that exceeds our grasp, that challenges us, that invites us to look deeper, to question more, to never stop seeking the truth. And maybe, just maybe, that's what time is really for, not as a river that carries us along, but as a framework within which consciousness can emerge, within which beings like us can exist and wonder and ask these impossible, beautiful questions about the nature of everything.